Christian Bauer, and he'll tell us about the Hamiltonian formulation of SUN gauge theory at large M.
So I thought, since I'm the last speaker, I thought maybe we can just also give the organizers a quick round of applause. Okay, yeah, so I want to tell you about some recent work of ours in Hamiltonian formulation of SUN gauge theory at large N. And in particular, I will talk here about goals. The goal here is to go towards simulating QCD on a quantum computer. So my angle is a little different of some of the talks we've heard in the past, but let's see where it takes us. So really the goal here, what I have in mind, is similar to what Martin Savage already started out on. We really want to have an idea of, or a way to calculate really the dynamics of the strong interaction non-perturbatively, from first principles. Okay, so the dream you might have at some distant future that we can just literally compute, say, the S matrix of some collision at the Large Hadron Collider. I can tell you probably this is going to be really, really, really far off because you need a lot of lattice points. But anyways, so that's sort of the ultimate goal. We want to get some, in principle, you could say in quantum mechanics, I create some initial state of protons, two protons, I time evolve them forward. They collide, they go to the end, and then I do some measurements, and that, the probability of observing a final state X, having started with this, gives me literally the probability to observe that event at the LHC, right? So that's sort of the really, really far goal that we have. So let's see where we are, right? So as I said, that's the goal. We want to simulate QCD, and I write here in more than one dimension, but obviously we want 3 dimensions. So that's the goal. But we're nowhere near. I think I made that clear. And so to make progress, we typically start with simpler theories. And so how can we make simpler theories? Well, we can look at simpler gauge theories. There's other gauge theories as well, and we can go to lower dimensions. Right, so let's just talk a little bit in 1D. We've heard actually a lot of discussions, and Martin sort of showed us a lot of results on 1D, and there's results on U1 gauge theories, SU2 gauge theories, SU3 gauge theories, and actually many other theories as well. In 2D, it actually starts, interestingly enough, there's not a lot of, so what I put here is actually implementations that exist, that were run on actual quantum computers. So there's lots of work here, but to my knowledge, it hasn't been run. There's also an interesting thing which I call 1D plus theories, which is sort of, it's in 2D, but it's sort of a plaquette chain. The reason this is a pretty big step forward to 1D theories is because you have dynamical gauge fields. You can't just integrate out the gauge fields. Okay, so this is a pretty significant step forward. And there's been quite a lot of work in SU2 and SU3. In full 2D, not just going really number of plaquettes in both directions. There's some work in SU2 that I've shown here, and then in SU3 I want to tell you what we have done, which is what this talk is about. Okay, and in particular what I want to show you, so the best previous calculation in SU3 was done really incredible work by Martin Savage's group. It's now, God, it's almost 4 years old. It's pretty amazing. So where they really did a really amazing setting up the whole way of formulating SU3 on a lattice, but when they actually try to run on actual computers, this is the biggest thing that they were able to run on. What I want to show you is a run that we did on quantum computers on a 7x7 plaquettes, but not full SU3. It's in that large N limit, and I'll tell you precisely what we did. So just so you can see, so this is the kind of calculation that was obtained by Martin Savage's group. So what they did is they prepared a system in the strongly interacting ground state of the theory. So essentially there's no electric field anywhere. And then they time evolved that system forward. And since this is the ground state of the strong interacting theory, and this is, I forget what G value they picked here, I didn't write it down, but it's not an eigenstate of the interacting theory, so they start seeing oscillations. And so they have an exact line. So this system is small enough that you can just simulate it classically. And what they showed, you can really get results out of the actual quantum computers. So this runs on performed on an IBM quantum computer. Here's the result of the work that I will talk about. It's very similar. We prepared also the state and the same state, and for reasons I can't remember, instead of showing the probability of being of having no excitations, we plot the probability of having at least one excitation. So we start at 0 and we oscillate around. And we did this calculation first on a 5 by 5 lattice, so 5 lattice points of 4 by 4 plaquettes, and then where we can have a nice fully analytical computation. You can see the simulation lies on top of it. And then we also did this on an 8 by 8 where we actually couldn't trivially get this classically. We had tensor simulations where we could simulate this theory. So I want to walk you through a little bit of what you do to sort of set up a calculation like this. And there's many things you have to decide when you put a field theory on a quantum computer. The first question is, how do you formulate? So first, the obvious thing is a full field theory is a continuous Hilbert space, infinite dimensional Hilbert space. We can't simulate that. We need to bring it down, and we need to do two things. We need to go in a finite number of spatial points, and then we also have to digitize the fields so they're not continuous fields anymore. Okay, so the first question is, how do we formulate a gauge theory on a lattice that reproduces SU3 in the limit of vanishing lattice spacing? And we can then decide, and I will obviously come back to this, whether we add any additional expansion onto that theory. But then there's many other steps you have to take. What is the basis you choose for your Hilbert space? Obviously, a calculation is basis independent, but it can have dramatic consequences of how efficient the calculation is. How to implement gauge invariance? We heard several discussions on that already over the workshop. Someone typically works in a Hamiltonian formulation, A0 equals 0 gauge, but that is not a full gauge fixing. So there is Gauss's law that has to be imposed. And how we do that, there's various different ways. And then this last step is this digitization, like how do we choose a discrete set of field value from a continuous field value? Those are sort of the steps you have to do. And then there's the last step that is important, like how do you actually encode all of that theory on a quantum computer? Okay, so the goal is to reproduce a Hamiltonian lattice theory that produces QCD in the limit. And I thought I'll take this paper, as Martin didn't really talk about it in so much detail. I think it's a really beautiful paper, and I want to walk you through these 4 steps that I showed you, what the choices were that these people made almost 4 years ago. So what is a lattice Hamiltonian to use? Well, that was answered. See, I'm not even giving a citation anymore. It's so well known. Kogut and Susskind did this about 50 years ago. So here's the Hamiltonian. There's an electric part of the Hamiltonian. That's essentially the Casimirs of the representations, and a sum over all links. And then I have a sum over all plaquettes in the lattice. And these are sort of the Wilson, like the plaquette operators that excite Wilson loops around single plaquettes. So that Hamiltonian is sort of the starting point for almost everybody in the field in one incarnation or another. The second question is, what is the basis you choose? And a very traditional basis that people use, mainly because gauge invariance becomes relatively simple, is work in a basis where the electric Hamiltonian is diagonal. So you work in a basis where E squared is diagonal, and E squared is essentially the generator or E is a generator of representation. So E squared is really the Casimir of representation. So what you want to choose is representations of the gauge group on the links. Now in SU3, we can, it's a rank 2 group, we can specify any representation with 2 numbers P and Q, and then the Casimir is just given by a well-known formula, and we also know the dimension of these representations. Gauss's law is the next thing, and again, we've heard some discussions about this. So essentially, I now have a representation at this link, a representation on this link, and all of these links. And what Gauss's law tells us is, so in E&M, Gauss's law tells us if I have no charge here, that the sum of all electric fields coming out is 0, the divergence of the electric field is 0. And I think several people explained this already very nicely. Really what this means group theoretically is that means the representations on all the links coming out of a vertex have to form a singlet under the gauge group. And so that means if I put arbitrary links or arbitrary representations, I need to make sure that Gauss's law is satisfied by sort of combining things with Clebsch-Gordon coefficients. Okay, so that can be done, and that has been worked out. And it's actually these Clebsch-Gordon coefficients, which are a huge pain in all of this. They're really hard to compute, and then if you go to large n limit, it's really hard to deal with. And then the final thing is you want to truncate the theory. So remember I told you Martin had a picture like this in his talk up already. So here are all the representations of SU3. And remember what a representation is the local energy at each link. So really what a truncation is doing, I'm limiting the total energy or the energy density that I can have on my lattice, because essentially as I go up here, the Casimir grows, so the electric energy grows. So we typically truncate somewhere here and only use the lowest lying representations. This is good in the strong coupling limit. It's actually a whole different story when you go to the weak coupling limit. And I'm not going to touch upon this, but there's actually quite a lot of work in my group on how to do that. Okay, so this were sort of all the choices that were made, and then what they've essentially could do is, like in a simple system like this, they could really work out the full Hamiltonian, do a qubit mapping, and actually put this on a quantum computer, and that gave these results that I showed earlier. So I remember I was really amazed when they did this work. It was really beautiful work. So what I want to talk about, but it's essentially, they make this comment, it is very difficult to go higher because they've essentially put all these Clebsch-Gordon constraints in my hand, and it becomes a global thing, and it just becomes essentially impossible to just keep extending this the way they did it in general. And so what I want to talk about, well, what if we add additional expansions in the theory? So what other expansion parameter do we possibly have in an SUN gauge theory? Well, we all know it's the expansion 1 over n. So the first thing that we did is we want to actually think about the representations in a different way, in a way that makes it a little bit easier to talk about SUN and the expansion. So let's just do, let's use some Young tableaus for a second. So here's a 3 representation. Here's a 3 bar representation. Here's an 8 representation. And let me essentially have for each box in my Young tableau, let me draw a line. And then so I'm essentially coming up with different graphical representation of Young tableaus. If I have 2 anti-symmetric boxes, I put this by sort of 2 double lines through here. So an 8 representation would look like a single line plus a double line. Okay, and then in SU3, it's special that a double line in this direction is the same as a 3 bar representation in the other direction. Now that's of course special about SU3, right? That is not true. So in SUN, it would be n minus 1 arrows is equal to the anti-fundamental. Okay, so this is just a way of sort of writing representations in a slightly cleaner way. And then we can start talking about, so let's look at again a lattice or a 2 by 2 plaquette lattice like this. And let's say I put 3 representations on these links, 3 bars over here, the 8 over here. That is just in that notation, just looks like this. Okay, so I have a loop that goes around like this, and then in here, I have an 8 representation. There's another state in my Hilbert space that I can write where essentially I have 3 bars everywhere here, and I could put a singlet on here. That is still satisfies Gauss's law because 3 cross 3 bar can give me a 1. So in my loop notation, I would just draw this loop here. There's also, I'm not even going to talk about this much, but there's something, let me not talk about this one, the point splitting. Let's just keep going. Okay, so that was just a, so this is just a graphical representation here. Okay, so now let's keep going. What are the possible states I can get? So the ground state in an interacting theory of the full theory that I'm interested in can be obtained by acting with electric diagonal or plaquette operators on the electric vacuum, the strongly interacting vacuum. The idea here is simply that I can get to the ground state of my interacting theory through an adiabatic evolution by starting with the ground state of the strongly interacting theory and then slowly adiabatically turning on the magnetic Hamiltonian. Okay, so I should be able to reach the ground state by this procedure. This is what I'm saying here. Okay, so now we can see, and actually the excited states with simplest topology you can also get by just require additional action of the interacting ground state with more electrical plaquette operators. But let's not worry about this. So a general state, therefore, in my theory, can be obtained by acting with an arbitrary number of plaquettes or plaquette dagger operators on the ground state, because that's all the Hamiltonian can give me, up to diagonal terms, which equals change phases in all of this. Okay, so let me actually label this state here by two numbers, P and P bar, and of course, for every plaquette, I have this. Okay, and now I'm going to say I have another representation of the Hilbert space, which I just introduced earlier. I tell you what loops do I have. So if you look at here, so here I tell you I have loops around the lattice, right? I specify all the loops in my lattice, and then I have to tell you whenever two loops meet, how do things combine into representation. So that's what this representation is. I specify all the loops on my lattice, and I specify all the combinations at the links. This looks like a really horrible basis, totally non-local. And why am I introducing this? Well, I'm introducing this because I can actually, in this basis, do a nice 1/n(c) expansion. There's a very simple relation you can write down if you take the product of sort of n fundamental operators, Q of those together, you can show that in the large n limit, you get this relation. Essentially, what this is using here, that the only way you can track the indices in SUN, and the n goes to infinity limit, you can't use epsilon tensors, because Q is always less than n. I don't have enough indices, so it's all delta function. Then you can prove this identity. Okay, so what does that mean? So now I want to say, so here's two of my loop states that I had earlier. Two plaquettes, which combine like this, or one big loop like this. So let's see if I start from, so remember, this is now my operator where I said I acted with one. So this is the state, the PQ a state that I had earlier. So this tells me I act on my vacuum with one plaquette operator here and one plaquette operator over here. And now I want to see what is the overlap with that state defined in my loop representation. And then the same thing here is, again, this is the same state here. I act with two plaquette operators here. And then what's the overlap with this loop state? And this you can now work out with this formula. And so graphically, you find that this one here is down by 1/(c). Let me give you a really simple way of seeing this. I put two plaquette operators. Here I have two closed loops. Gives me n squared. This is down by 1/n because I only have a single loop with n running around. Okay, so you can easily convince yourself that this state is down by 1/n. And if you work this all out, you actually find that that you can write a very general expression between these states that I had earlier in these loop states, namely that the expansion of these states goes like this, where mi is the number of plaquettes encircled by each of the loops. Okay? And so you can see the only way I can get a leading order result if all mi's are 1, which means that every loop encircles at most one plaquette. Well, it has to circle at least one plaquette, and at most one circles exactly one plaquette. Okay, so to leading order in 1/n, you only have states with a loop encircling single plaquettes. So now let's try to put this on a lattice. Okay, so this is a state that I could have. You know, there's a loop encircling this, one here, two loops encircling this, and so on. So let me make one more. Yeah.
But the counting of loops that are larger, I mean, don't we have to worry about the fact that there's many more of them?
Yes, but I think in the strict 1/n limit, it doesn't grow with n. It grows with the volume of the lattice. Right? So now let me make one more step. So far this was all large n. So let me make one more step in order to put this on as easy on a quantum computer as I can. So remember, I also told you I have to truncate the representations that I can have. And so let me truncate all these representations on the links to only include the 1, the 3, and the 3 bar. Okay? So in other words, I'm truncating the Casimir, the energy density. So since this is a single loop, so here, this has to form either an 8 or a 6 or a 6 bar. And so I cannot have two plaquettes that are actually next to each other. So this is not possible. This is not possible, okay? So all I can have is plaquettes that are separated at least by 1, okay? So this what comes, but this comes out of the truncation. That's not something that comes out of large n, that comes out of my truncation. We do one more thing, that there's a charge conjugation symmetry, so let's actually look at only the even, the C even sector. And so I'm sort of really, when I draw a loop like this, it's the loop in one direction and the other direction summed over. Okay, so that now gives me, once I have this, putting everything together, what I just told you, there is two possible states each plaquette can be in. Either it's no excitation or it is one excitation. It's actually, what I mean by one is really the sum of the loop going this way or the other way. And secondly, neighboring plaquettes cannot be excited at the same time. Okay, so what is the Hamiltonian that I get from this? So first you work out, so here's the Hamiltonian. Let me walk you graphically through what this is. So this tells me, so P says that's a projector. So I'm summing over all plaquettes. So notice I'm only summing over plaquettes now, not links, only over plaquettes. And so if a plaquette is excited, then each link gives me 4/3, the Casimir of the fundamental. Okay, and I have 16/3, and there's a 1/2 g squared in front. That gives me the 8/3 g squared. And then this term here says I can flip, my box operator can excite a plaquette or de-excite a plaquette, but only if the neighboring plaquettes are not excited, right? If any one of these plaquettes is excited, I cannot excite this one, and vice versa. If any one of these is excited, this couldn't have been excited in the first place. So that means my Hamiltonian, and there's some 1/√2, and there's some diagonal piece that you get from this, but really what that says is I have an X operator at plaquette P, and then but multiplied with projection operators at all the neighboring sites that they have to be in the ground state. Okay, so that's my Hamiltonian. And it looks very similar to PXP Hamiltonian, which we've also heard. So the interesting question is now, how do we implement this system on a quantum computer? And so here, the difficult interaction is this. Okay, so we need to do a flip that is dependent on 4 neighboring things. So it's a controlled operation, controlled on 4 other qubits. So here's the latest and greatest, at least at the time when we did our paper, of what a typical qubit layout looks like. Okay, so let me try to put this, put some lattice. Okay, so here's now my lattice. So everything here at the center would be my qubits that I'm going to use to represent the plaquettes. Now, one thing you notice is, so let me highlight this. Let me make it a little bit clear that all these plaquettes that actually are physical qubits and encoding a plaquette, let me put them in circles, and all the other plaquettes, all the other qubits that that were lying here, they're not really used directly to encode the system. Let me put them in squares. Okay, so the problem is, I want to put this interaction on here. So let's put this. So let's say I want to have this interaction here. Well, I have a nice connection. First, this guy is not connected to the yellow guy or this guy. There's something else in between. And even worse, there's no direct connection to the qubit at top. So how do I actually physically encode this on a quantum computer? And there's actually a cute little trick that you can do. Namely, so if you see sort of all of these, so if you look at this thing, there's this yellow guy and this yellow guy sort of connected with 3 of these other qubits. And so what you can devise a circuit, I'm just going to draw it down, doesn't really matter. What this circuit will do, that if you start with all green plaquettes in a 0 state and both yellows are in a 0, then that flips all of the greens to 1 state. And if any one of them is not in a 0 state, all 3 of those stay in a 0 state. You can show, and it's very, very easy to show that this circuit will do. So that really means that if I now have this system here, so remember I wanted to be able to flip this qubit if all 4 of those are in the 0 state. So I'm first going to run the circuit that I just told you. That will flip all of these qubits to 1 state, and then I just control directly on here. So it's a doubly controlled operation. Okay, so that's how we implemented this calculation. That's what gives me these results here. And then what we also put on here is we did a calculation in that 1 plaquette chain that we could actually do in using the full simulation that Martin Savage worked out. And this is that sort of teal color, green, teal, whatever. That's the full theory result. And this is our result in the large N limit. So it's order 20%-ish as you would expect. Okay, so that's really what I wanted to show you. So I think adding a 1/NC expansion really dramatically reduces the available Hilbert space. It dramatically simplifies the Hamiltonian. Now that's of course not so surprising because we heard lots of talks that the physics in the large n limit is a lot simpler. And actually, I think there is, yeah, I'm almost done, the second to last slide. And I think this is actually not the end of the story. There's lots of things we've done since where I think you can simplify things even more. But I'm not ready yet to talk about it. And I think many of the things that we heard here in this conference, we see in our setup as well. But this has really allowed for first simulation of SU3 Young-Mill gauge theory on digital IBM quantum computers in 2+1D. Actually, I do want to show you one more thing since I have the 5 minutes. So here's the Hamiltonian I just showed you. Okay, so here it is. This is just what I had earlier. Let me show you a different quantum system. Different Hamiltonian. Okay, this is some Hamiltonian. There's some if some state is an excited state, there's some delta energy. There's some X splitting, and then there's something that is sort of is a 1 over d to the 6, or some term that depends on the if two qubits are in a 1 state, then essentially I'm getting a negative term depending on the distance of these two from each other. Okay, why is this Hamiltonian interesting? Well, this is the Hamiltonian that Lucan has in his lab at Harvard. Okay, so writing 10 Nature papers a year or something with this Hamiltonian. Now, what I'm going to tell you is that those two Hamiltonians are actually essentially the same Hamiltonian. Okay, and so the easiest way for me to show you this is we've coded up their Hamiltonian, we've coded up our Hamiltonian, and we just time evolved the system. Okay, and so you can see, so what we did here is we created, I think, a string. So we put two fixed charges on here that created a flux string, and then we let the system evolve. And sort of, you can see that, it's not the same, but it's actually very similar. In look, and you can actually show, so essentially what you can show is that, that this term is called the Rydberg blockade. That essentially is mimicking that PXP term. So really the way you should think of this is if two neighboring qubits are both in a 1 state, there's a huge detuning of my laser that's happening, and therefore I cannot actually excite something if the neighboring state is in the 1 state because my laser is just detuned. Okay, so that's really what's going on here. So I think this is super exciting. We're working with the Lucan group at the moment to put this, and that would be an analog simulation. Right? I'm not talking about digital computer. It's an analog simulation of QCD. Well, SU3 Young-Mill's theory is truncated extremely hard, blah, 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 blah. I always say QCD, and then people always remind me that fermions are part of QCD. Anyways, so there's lots of things known about large N. So this is really just the beginning, right? We heard in this conference, there's lots of things known about large N. How can we better connect to those results? And as I said, I think if I would give this talk a little bit later, I could tell you a lot more interesting things, but I'm not quite ready yet because I really want to make sure I understand everything here. This is just what I just said. To describe QCD reliably, there's many other things we need to do. We need to raise the truncation. We can't just say we only have the fundamental representation and so on. We need to probably need to include higher orders in 1 over n. We probably want to include fermions. Well, not probably. We need to include fermions. The last thing is, so far we've focused on superconducting digital and analog neutral atoms to actually do the simulations. What we really want to study are there other systems, for example, trapped ion systems, which have all-to-all connectivity that might be even better. In particular, once you go to 3D, it becomes really hard to get connections in 3D on both neutral atoms and superconducting devices, whereas trapped ions have all-to-all connectivity. So one of the things we're thinking of doing, sort of using trapped ions to do really small scale 3D simulation of this. So that's really, this is really all I have. So I think this is sort of, our first baby step maybe to really go towards simulating QCD through a systematic expansion, really going beyond just sort of 2 plaquettes, but really scaling to size. Thanks.
Yeah, Victor.
Is it possible to take your truncated theory, this 1 over n and truncated representation, and then just do some Monte Carlos to see if this theory is actually similar to Young-Mill?
Yeah, so we have in some easy cases, we can actually use Monte Carlo. I mean, at somewhere there's a sign problem, right? So we have to be, so this theory is not so easy to do, but some static quantities we can do. And there we do agree with those simulations. I mean, I should mention, right, to get these results, from the machine. I mean, so we can show, of course, we can simulate and show that things.
I didn't mean to simulate your quantum thing. I meant to like try to see how that theory, how similar it is to actual Yang-Mills, like to take a truncated theory and measure some observable and Monte Carlo is measurable.
The problem is, of course, where this is interesting and is for real-time dynamics, which we can't do Monte Carlo for. But yeah, I'm sure there's many more things you can compare than we did. I mean, we took one observable and there we showed that you agree. You know, there was this plot here, right? So, I mean, it's a lattice version of a theory, but this is sort of, I mean, this is not the large N limit at the top here.
Can you comment a bit more on the choice of the electric field basis? So you have your electric Hamiltonian diagonal there. The reason was that you could map it on 2 qubit gates and.
Yeah, I mean, we choose here the electric basis just because it's mainly because right. So I got a lot of mileage from drawing these closed loops, and that's essentially that relies on representations, and so working in these in a representation basis, in what is called an era basis often, which is also the electric basis, makes things a lot easier. I should say, you know, one thing that is important to say that if you really want to go to the continuum limit, we heard this many times, you need to go to small coupling, not large coupling. And so it's a question what kind of truncation you need to do. I've totally unrelated to this work, I've done quite a lot of work on working with magnetic bases, and I actually believe we can use the same large N ideas in these magnetic bases, because we sort of showed a relation between, we sort of have something what is called a mixed spaces, or sort of half electric, half magnetic, and so I believe at some point I can come back and show you results in a magnetic basis, but we also expand around the large N. But I haven't done that work yet, so I don't know. But yeah, the reason here was just, it's electric basis is the simplest basis to just deal with Gauss's law and engage invariance.
So it's strong coupling, there are relatively few excited plaquettes, and then as you go to weaker coupling.
Exactly. So what you'll find is there's more, so right, the electric energy is the number of plaquettes excited. And so if the electric Hamiltonian dominates, then that gives me a very highly excited state. But in the weak coupling limit, it doesn't cost me, I mean, right, the electric energy is very much smaller. So what you'd expect, the sort of the ground state is now some, so what you find is a function of G, the ground state is a, you know, the support of representations grows, or the support of Casimirs grows, you know, or if I plot like Casimir versus amplitude or something, and then I plot as a function of G, as I drive G to 0, that will get wider and wider. And so I need to include more and more representations in this. So this will become difficult. Now the question is always, what coupling do you really need in order to do the extrapolation to the continuum, right? So there is discussion. So I think the jury is out, like whether an electric basis will be able just be fine enough to go to the kinds of couplings we need to then do the extrapolation. But I think people really haven't.
Are you working on a torus? Or on
This one was open boundary conditions. It's essentially, but this is mainly, for us there's no, but it's, you notice there's just no connection that goes from here over to here, right? If IBM would give me a chip on a torus, I'd be very happy to run on the torus.
But when you just solve it on a usual computer, you can try it.
Yeah, so when we simulate, we could set this up. I mean, we did not because we wanted to go in the hardware, but it would be relatively straightforward to set this up with periodic boundary conditions.
So this is ideally set up for 2 + 1 dimensional problem.
Ideally what we'd want is, you know, all connectivity everywhere. That's actually something else we're doing. If Amazon has a chip that really has connections essentially just like a lattice, which we're going to try out and see what we can get from that. But of course, the end of the day, so, this looks great, but really what we need, at some point I need more representation, so I can't just have a single qubit per plaquette. I need multiple qubits per plaquette. So really the ideal system would be a QDIT system. So you have, a state with n levels at each point and then connected, which is not, in trapped ions, people do have QDIT, so it's not out of the question. But I think a really interesting area of research here is really you have to get theorists together with experimentalists to really figure out, well, what is the kind of hardware that we need to do these kinds of simulations? Goes under the name of co-design. And so I think that's really important, and we'll have to see where this takes us.
Yeah, speaking of raising the representation cutoff, do you understand if there's a way in general, if I have, I don't know, SU5 and some copper representations, can you make some game out of excited plaquettes and how many you can have neighboring and things like this? Is this generalized?
Maybe. We haven't yet fully tried. We are so in the large n limit, the nice thing is in these loops, the representations is, there's several really easy things. Like, for example, the Casimir is just literally the number of boxes in the Young tableau, which is actually really important, right? So what I showed you at some point I told you that, right? So remember there was a sum over links before, now I have a sum over plaquettes. The reason I could do that, because each plaquette gives me 4 of those, but that is only easy if it's linear. If it's actually quadratic in n, then it doesn't work anymore. So that was pretty important, that linear. But yeah, so I think in large n you can do things. The counting becomes quite easy in these representations. Now there's of course other things that you have to figure out in SUN. You can get representations that just really don't exist in SU3, right? What is just because I'm using an SU3, like 3 boxes underneath each other is a singlet. That is not true in SUN. So I think you have to figure out how to deal with that problem.
So even for SU3, if you want to include the 6, you have trouble with this 6 representation. This term becomes more troublesome.
We are at the moment thinking about how to do that. And so what you find is, for example, the 6 and the 6 bar have the same number of boxes. They have the same Casimir at leading order 1 over n. They have different Casimirs. Well, not the 6 and 6 bar, whatever which one is the one that 2 next to each other versus 2 above each other? I forget. Is that a 10? It's not a 10. Which one is it? Anyways, there's 2 representations. This representation, Young tableaus. This one, and I guess, sorry, that's the 3 bar. Yeah, 3 bar and 6 have the same. Well, in SUN, this representation have the same Casimir. Of course, in SU3 they do not, which already tells you there's a 1 over n correction.
Anything other than n, they have the same.
They have the same Casimir. It's literally the number of pockets, it's like n, both of them. Yeah, and so yeah, I think you can play that game.
Any other questions? Well, let's thank